So we're ready to start a whole new unit, a whole new set of ideas today. And this is, in some ways, what we're going to do in chapters 9 and 10 are really the end of, I guess, what I would call kinematics. Okay, that we've talked about motion, we've talked about our chapter 2 equations, we've talked about forces, we've talked about energy, and now we're going to talk about momentum. And when we get to chapter 11 and 12, we're going to take everything that we did in chapters 1 through 10 and cover it again, except for things that move in circles. So it's going to be interesting. And then the last couple chapters are something totally different, but this is kind of a bookend of a sort. So as we've gone through the kinematics problems, and I'm not sure if it was you guys so much, but in many other years when I've taught this class, when we let something drop and we talked about what its initial velocity was and the distance that it fell through and what its final velocity was, people often want that final velocity at the bottom to be 0. And if you recall, I never let you do that. Okay? Because we're always talking about what happens right before that impact. Because unfortunately, during that impact, the forces aren't constant anymore. And if you remember our chapter 2 equations, we had to have a constant acceleration. And how do I get a constant acceleration? By having a constant force. So what chapters 9 and 10 let us do is talk about a little bit about what happens during that actual collision. But it also lets us talk about what happens right before the collision and right after the collision. So it's going to expand the way we can talk about the interactions between objects. So we've got to cover some things first, because we're going to need those words later. And the first thing is center of mass. So the official definition is that the center of mass of a body or a system of bodies is the point that moves as though all of the mass were concentrated there, and all the external forces were applied there. Okay, so the center of mass of a body or a system of bodies is the point that moves as though all of the mass were concentrated there and all the external forces were applied there. Now, as with many things that we do in physics, there's the official definition that you find in the book, and then there's the more practical way of thinking about it. So another way of thinking about the center of mass is thinking about it as what I would call the balance point. So take a pen. If you're using a pen, your stylus is not the best choice. So you should probably get out a pen, okay? And figure out where you have to place that pen to balance it on your finger. It takes a little work. You might have to angle your finger a little bit. You might have to put it on a specific part of your finger. Like if you put it in between your knuckles, sometimes there's a little bit of a dip. Okay, that'll work too. Okay, so for some of you, like Casey, it's pretty much in the middle of the pencil. Okay. Maddie has a cap. What if you put the cap on the other side of the pencil, of the pen, like I'm going to do? Did it move? A little bit. Okay. So the center of mass has to do, well, it's a balance point. Another way of thinking about the center of mass is we don't see this a lot because most of the things that we've been throwing around figuratively in our problems have been balls or boxes. Okay, and if I throw the pen straight up, doesn't really do anything, right? Just goes up and comes down. But if I give it a little torque at the beginning, then the pen turns end over end as it goes up. But if you look at the center of mass of the marker, that center of mass makes the same parabola that we're familiar with. Okay, so even though the pen is twisting and turning as it goes through the air, the center of mass still moves through the same parabola as if I had tossed up a ball. Okay, because the gravitational force is acting on that center of mass of the pen. Okay, make sense? At least you can imagine it. All right, so let's talk about how we find the center of mass. And finding the center of mass really depends on how the mass is distributed. So for the pen, the cap is usually the heavier part. So as Maddie and I observed, when we moved the cap of the pen from one end to the other, the center of mass shifted towards where that cap was. Casey had a pencil, and it was pretty much in the middle, but it was actually, if you looked carefully, shifted a little bit towards the eraser and that metal piece that holds the eraser on, because that's going to be a little more mass than the uniform wood of the pencil. So let's figure out how we would talk about this. So we're going to start with a very simple system. So we're just going to consider two particles separated by a distance d. And of course, because this is a science class, I'm going to put them on an axis, because why wouldn't I? And I'm arbitrarily going to put M1 at the origin and M2 over here. And these particles, like my problem says, are going to be separated by a distance d. So I can say that x1, the position of M1 is 0, and x2, the position of M2, is going to be d. Okay. So if M1 equals M2, where would the center of mass be? D over 2, which would be the middle. Okay, so the center of mass would be in the middle between the two particles. And we kind of denote that coordinate as xcm, and it would be d over 2. If instead m2 is bigger than m1, where would the center of mass be? Where would it shift? Towards m2. Okay, and if m1 was bigger than m2, which way would the center of mass shift? Towards m1. Okay, so the center of mass is always going to be towards what the bigger mass is. So in this case, I might define the center of mass by saying it's m2 over m1 plus m2 times d. And I can see if that definition makes sense. If m1 equals m2, then what am I going to get for xcm if I use this formula? Choose m1 or m2 and substitute in for it. Yeah, I'm going to get 1/2 d, right? Because I'm going to have m2 over m2 plus m2 times d, or m2 over 2m2 times d. Those m2's will cancel, and it'll give me d over 2, which is exactly what we predicted, that if the masses were equal, the center of mass would be in the middle. Make sense? Okay, so we could take another extreme case here. What if m1 was equal to 0? Then where would my formula say the center of mass was? D. Okay, which again, I think makes sense. If this mass goes away, all my mass is over here, so the center of mass would have to be where all my mass was. Yes? Okay. And finally, as you might assume or guess, what if I let m2 be equal to 0? Then what does my formula say that the center of mass should be? 0. And again, I think that's makes sense, because what's located at 0? m1. So all the mass would be there, and that would be where you would expect the center of mass to fall. Now this is all well and good when I've only got 2 masses, and I can put one of them at the origin. It makes things pretty simple. But when in life are things really that simple? Never in physics. Okay, so we need to expand this a little bit. So let's take a system of many particles. I'm going to call it n particles, just so that we can make it something bigger. With mass mn and located at positions xn. And just so that I know that I'm talking about the general case, I'm not going to put anything at the origin. So I'm still going to draw my axes, but I'm going to let M1 be here at X1, and here's going to be M2 at X2, and here's going to be M3 at X3, and here's going to be M4 at X4, yada, 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 and out here somewhere is going to be my last particle, Mn, at Xn. Okay. So if I have all of that, then I can say that the x-coordinate of the center of mass is going to be m1x1 plus m2x2 plus m3x3 plus adding them all up until I get to mn xn. And I'm going to divide that by capital M, where capital M is the total mass. So it's the summation from I equals 1 to m of each of my masses. Okay, do we remember how to deal with summations? Vaguely. It just means, so this is equal to, well, let's write everything down, and then we'll talk about what it means. I am excited for grilled cheese. This has been a very good week of food, so I'm very curious what we're going to have tomorrow. I could look, but... All right, so this summation thing, all right? This symbol, which is actually a capital epsilon, means summation. And summation means you do what? Yes. And what does sum mean? You add them together. Okay? So whatever is after that summation symbol, which in this case is mi, I'm going to add together all the m's. The I is what I call, and everybody else calls, the index. And at the bottom of this summation, it tells me where to start my index at I equals 1. And at the top of this summation, it tells me where to end my index, where I stop counting and adding things together. So this would be M1, because that's the beginning of my index. And I run through all the whole numbers until I get to my final index number, which is n. So that's going to be M1 plus M2 plus M3 plus dot, dot, dots, all the way up to Mn. So it's really giving me the total mass of my system. It is, but sometimes, but I can use this summation thing, and the thing that comes after the summation can be more complicated. And in fact, we will use this symbol again in calc when we're talking about adding up all of the little rectangles or all of the little trapezoids when we're finding the area under the curve. So it's really a very useful shorthand once you understand what it means. Okay. So note, if we go back to the formula for center of mass, that each of those positions for a particle are weighted by what the mass is. So if M1 is really big, that's going to heavily weight its position and move the center of mass closer to where M1 is, which is at X1. Okay. We should also note that my big formula up here will simplify almost to the formula we had before if I only have two particles. In my original example, I put M1 at the origin, so this term really went away because X1 was equal to 0. But this gives me my much more general case. Okay. Make sense? We got it? Got what we need? Not quite. Okay. All right. So, of course, as we've done with everything else, I can take it from one dimension and put it into 3 dimensions. So, while I have this expression, see, and I'm going to use it again and make it easier. For my x center of mass, it's 1 over m times my summation from I equals 1 to n of mi xi. Instead of writing out m1 x1 plus m2 x2 plus m3 x3 plus dot 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 plus mn xm n, okay, I can write it this way. And this just tells me that what I'm doing is I'm adding up all of those things in pairs, okay? And I can have a similar expression for the y coordinate. And I can have a similar expression for the z coordinate. We don't often use 3 dimensions. We will do an example, maybe today, maybe tomorrow, where we've got a 3-dimensional object and we need to find the center of mass. Most likely it's going to be a bunch of particles scattered around the xy axis, and you'll have to figure out where the center of mass is. Now, of course, because this is physics, I can turn this whole thing into a vector. So if I consider each particle to be at xii plus yij plus zik, then I can write the center of mass vector, position vector, as x center of mass I plus y center of mass j plus z center of mass k. R is the position vector, so it gives you the x, y, and z coordinate, like we did way back at the beginning of, oh, I don't know what it was, chapter 4 maybe. That's usually a capital R. Kinda. And then I can make this a little more of a shorthand by combining stuff. And I get 1 over m index from I equals 1 to n of the mass of each particle times its position vector. A little bit of this is, I need to show you a bunch of things in case you come across them, but in reality, the problems that we'll solve and the problems you'll be presented with will be a lot simpler, but I can't let you out of here without showing you some stuff, so that when you come across it next year or the year after when you take physics again, I hope you're not, oh, I don't know what that is. It'll be, oh yeah, she showed us that. So, yep. It's a little more complicated than that, but well, and actually it's a nice segue to what I want to talk about next. When we do this, when I do this in well, okay, we will do this later on when we talk about gravitation. Okay, and in fact, actually, the sample problem that we do is finding the center of mass of the Earth-Moon system. Okay, so if you wanted to take kind of an entry level, a beginner's level, a first order approximation, you could consider each of the planets to be a point source, which would make sense because they're all pretty far apart and you're going to be pretty far away from them. And you would have to get yourself a snapshot of what the solar system looked like right now, because it's never, I mean, I suppose statistically, yes, at some point it's probably the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all in a line, but in reality, it never looks like that. Okay, so you'd have to take your snapshot of the solar system, which, you know, you'll have. Yeah, you could. Exactly. But all you need to know, so if that's going to be the sun, you know, here's going to be Mercury, here might be Venus, Earth would be over here. You'd probably have to do it in 3D, but all you need to know are the masses of the planets and what might be called the radius of their orbit or the semi-major axis of their orbit, and you can find it. And what you'll actually find is that the center of mass of the solar system is right there. Because the sun is so big and so massive. And it's actually a way that you can find, because it's not right in the middle of the sun, mostly because of Jupiter, because Jupiter's pretty big. So instead of, when you have a system like this, we think of it in our first order approximation as everything orbits around the sun. If you ask anybody on the street, if you ask anybody in this building, even people who have survived astronomy, they'll tell you that everything orbits around the sun. It doesn't technically. Technically, everything in the solar system orbits around the center of mass, which happens to be really close to the middle of the sun. So the sun orbits around the center of mass too. So instead of the sun orbiting like this, okay, where I'm turning on one spot, okay, like I'm trying to turn around the spot in between my feet, what really happens is the sun is kind of making a tiny little circle. But that tiny little circle, like the center of that circle is really close to the center of the sun. So you don't see the sun moving, but what happens is the sun, you gotta love it, wobbles. And that is a technical term that Marcy and Butler coined in the 90s. I was actually at one of their first like little 10-minute presentations that they did about it at a conference. And they found actually a whole bunch of exosolar planets, so that's planets that orbit around other stars, because this wobble, so now if I'm just orbiting on my axis, I'm not really moving towards you or away from you, but if I'm orbiting around this little spot, then sometimes I'm coming towards you, which means my light is what? Nope. Nope. Well, vaguely. If the source is approaching you as opposed to the source moving away from you, duh. When the ambulance comes up from behind you, it's a Doppler shift. So when I'm coming towards you, when the sun is making that part of its movement, the light is blue shifted. When it's moving away from you, that light is red shifted. So you see this tiny, sometimes it's enough that you can actually see the star move, which is what the wobble really is you can actually see the star moving its position if it's close enough and if it's big enough. If the movement is big enough. You can also, they later on went to use the Doppler shift that you could tell that the star was moving. So when they first started finding planets, all of the planets that they found were huge and were nearby the star in the middle, because you had to, they were even bigger than Jupiter, and they were orbiting at radii of like Mercury. So they were gas giants. There was no chance there was going to be life because they were too close to their star. But they were big enough and close enough that they shifted the center of mass enough that you could actually see the star move, and so the star wobbled. But that's why originally all the planets that we found were uninhabitable, because of the way the search was done. And then as telescopes got better, Marcy and Butler were able to look at smaller and smaller wobbles, and then they expanded their way into other ways of looking for stars, or looking for planets. So Jeff Marcy, and I can't remember what Butler's first name is because he's apparently not, I don't know, like if you watch a documentary on exosolar planets, Jeff Marcy's going to be in it. He will be, because he and Butler are the founders, the beginning, the parents of finding exosolar planets. But for some reason you never see Butler. I don't know why, but it's always Jeff Marcy. So anyway, that's why center of mass is important. Well, what do you, okay. A rotation is different than an orbit, because I can tell you what the rotation of the sun is. Rotation is moving around your axis. So the rotation of the sun is about a month, it's about 28 days, depending on where you are on the sun, because different parts of the sun rotate at different rates. It's called differential rotation. I honestly don't know. Yes, there are places where a day is equal to a year too. Most things rotate faster than they revolve or they orbit. Like it takes Jupiter about 10 hours to rotate, but it takes it. No, we could figure it out. 5. What's the square root of 125? 11. It takes it about 11 years to go around the sun. I have no idea how long it takes the sun to do that little thing. Yeah, I have no idea. And I don't know if that's the right question to ask. You might want to ask you could try the orbital period of the sun, and you might get something. Yeah, see, that's what I was afraid of. But for what? How long it takes to go around what it Yeah, but I think it's around the Milky Way because not a that I wonder I don't know if we can figure it out. Yeah. Yeah, no. We'll come back to that. We'll talk about that in chapters 11 and 12. It's how they have to go at different speeds because they have to make the same circle. They have to make different circles in the same amount of time. So if you're farther away, so if I go like this, my shoulders are moving at a different speed than my hands. Which is, I remember. Yeah, I have a copy of that, like cut out from the newspaper, because I was old enough to recognize it. I think I was in high school when it came out. Okay, so let's see if we can do one more thing. Intellectual curiosity has taken us away, but that's okay because it was a really good conversation. However, to go back to center of mass, you should know that very often particles are not discrete. They're not separate little things. Okay? That much more often in our lives, we have continuous objects. You are a continuous object. If I wanted to find your center of mass, it would be very difficult for me. I'd have to take every particle in your body and map it somehow and then do that whole summation thing. So that when I equals 1 to n, n is going to be like millions. Okay? And so that's not going to be practical. So we can also talk about the center of mass of a continuous distribution. And this is another thing where you might get kind of scared, but then we're going to make it easier. Okay? So if I consider a sphere, I'm going to take one tiny little piece of that sphere, one little point. All right, we'll have to do it. We'll do it tomorrow. All right? Well worth the distraction. Well worth it.